Okay, so this is the third and the final talk of this afternoon session. We have Jörg Teschner from University Hamburg. He was going to talk about quantization of modular spaces of flat connections and Liouville theory.
Yeah, thank you very much for the introduction, and thanks very much to the organizers for the kind invitation to present a talk here. And before I start, I want to say that some part of the work were done in collaboration with Grisha Vartanov. And let me start by mentioning some of the motivations which originally brought me to the subject. Perhaps the first and oldest, in a sense, was nicely presented in Bertrand Duplanty's talk. So it is two-dimensional quantum gravity, which has been a challenge and a focus of interest in mathematical physics for quite a while. And what's also nice but also amusing to see is that the approach I'm going to present, I'm not going to present the link to the quantum gravity as discussed in Bertrand Duplanty's talk very explicitly, but I can assure you that basically what I'm going to present can serve as basically the building blocks for a completely independent approach to the study of two-dimensional quantum gravity. It basically gives the building blocks from which the answers can be assembled. All right, another topic which motivated originally this kind of research, in particular the study of Liouville theory, is conformal field theory, in particular non-rational conformal field theory, which is a class of conformal field theories vastly extending the much-studied class of rational conformal field theories. The Liouville theory that we're going to discuss represents the simplest example, and in some sense, mathematically, you can understand the passage from rational conformal field theory to be somewhat analogous to the passage from rational conformal field theory to non-rational conformal field theory to be somewhat analogous to the passage from the harmonic analysis on compact Lie groups to the harmonic analysis on non-compact Lie groups. And we will see some elements of harmonic analysis during the talk. So this was something which made me study it for a couple of years, around say 2000. And I then temporarily abandoned the subject a little bit. What made me return to the subject more recently was the so-called AGT conjecture, an amazing relation between four-dimensional supersymmetric gauge theories and two-dimensional conformal field theory, which in mathematical terms amounts to relations between the equivalent cohomology of instanton moduli spaces and, the two-dimensional conformal field theory, or in mathematical terms, the representation theory of Virasoro algebra, or more generally W algebras. So this is what in the years from say 2009 say to 2013, when I published the work with Grisha Vartanov, made me finish some of the business that was started around 2000. All right. So now, now I switch gears a little bit and turn to the mathematics, which were relevant. And what I want to stress is something which, to my amusement, was also very much stressed by Kurt McMullen in his laudatio for Miriam Mitsakani, namely that the Teichmüller space has two faces. And this was very important, as Kurt McMullen stressed, for Mitsakani's work. And, in a completely different guise, also appears to be foundational for the story I want to tell here. So the two phases are as follows. So we're talking about the Teichmüller spaces, which are, the spaces of deformations of complex structures on Riemann surfaces, to introduce them in a concise way. So what we shall consider are two-dimensional surfaces sigma of genus G with n punctures. And the two phases are, the Teichmüller space can be thought of, on the one hand, a space of hyperbolic metrics of constant curvature on the surface modulo diffeomorphisms, or on the other hand, a space of deformations of complex structures, as already said. And the relation is just the classical famous uniformization theorem. Namely, given the complex structure on sigma, well, this is equivalent to putting an atlas with local holomorphic coordinates, say denoted yi onto sigma. And with respect to this atlas, I can look for a metric which is just conformal to the standard metric associated to this complex structure, which has constant negative curvature. And written out, it means this function phi, which locally describes the metric, has to solve a partial differential equation, which is in fact nothing but the Liouville equation. So this is somehow how what is called Liouville theory connects to the theory of uniformization already early on, maybe on the level of classical equation of motion. That is what we see here. Okay, so and the statement of the uniformization theorem can be restated by saying that such a metric exists for any given complex structure and it is unique up to diffeomorphisms. And what will be useful to know, to have yet another useful picture of that, is that there is also associated to such hyperbolic metrics a flat connection, a natural flat connection, which can be represented by splitting it into 1, 0, 0, 1 parts as follows. The 0, 1 part is just trivial. The 1, 0 part can be represented in this form, where t is related to this function phi, parameterizing the metric of constant negative curvature in this way. And so then this equation ensures, in fact, that this function t of y that you construct in this way is holomorphic. So this is a consequence of this equation, of the partial differential equation, which gives the uniformizing metric. And so, okay, and holomorphicity, of course, ensures flatness of this connection. Well, furthermore, what is known is that the flat connections which come from uniformization in this way, they fill out a connected component of actually the full dimension in the moduli space of flat PSL2R connections on sigma. So this is why essentially the space we're talking about, the space, the Teichmüller space, can also be thought of as a component in the moduli space of flat PSL2R connections. And well, this is a perspective which sometimes is useful. All right, so what's important about these two faces of the Teichmüller spaces is that the structure of the space we're interested in, which is the Teichmüller space, so it reveals two rather important structures that this Teichmüller space has. So the first, which is called A model, representing it in terms of hyperbolic metrics, is well, it exhibits the Teichmüller space as a real slice in an algebraic variety, which is called the character variety. Here is the rough definition. So it's the space of representations of the fundamental group of the surface into SL2C modulo overall conjugation by matrices in SL2C. And well, this is very important. In particular, it's very important that it gives it some algebraic structure in this way. And secondly, there is a complex analytic or even Kähler structure of this space, which is well, of a rather different nature, as it turns out. And somehow the interplay between these two structures, this is what Kurt McMullen was emphasizing, and this is what is going to play sort of a key role for the story I'm about to tell. And in fact, it was also amusing for me to see that in Bertrand Hénard's talk, it was coming up in one way, and furthermore, the association to A and B model that he had in his talk is exactly the one that I have here. All right, so to begin, we shall begin on the A side, the A model side, where coordinates are provided by what is called the trace functions. So we take an element of the fundamental group, well, we associate to it a matrix in SL2C. I mean, this is what this homomorphism does, and then we take the trace. Thereby, we have something which is already invariant under this conjugation in SL2C. And what is known is that the ring of algebraic functions on the character variety is generated by these functions, considered as functions on this space. So this is of course a complex variety. However, it has a natural real slice where basically just all these matrices representing elements of the fundamental group are real. And so we can therefore restrict all these functions to the real slice, and the restriction of these functions to the real slice, or more precisely the Teichmüller component of it, I mean it breaks in a finite number of disconnected components, this is what can be identified with the so-called length functions, because these are simple functions of the geodesic length of the curve, which is of a geodesic isotopic to the curve gamma. So these are key players. I mean, just the very basic variables describing basically the algebraic structure of the character variety. Now, the game will be to quantize that. And well, let's recall the algebra of length functions is basically giving the coordinate ring of the character variety, and what we shall do is to deform these algebra of length functions into a non-commutative algebra denoted AH bar. What we do in this way is basically we deform, but also in a sense unify two important structures of A. Namely, the structure as an algebra, we can multiply the length functions. And secondly, as a Poisson algebra, namely there's a natural Poisson bracket on our space that was introduced by Goldman and Attia and Bott and so on. So this is deformed and unified into a non-commutative algebra AH bar, such that if I take the non-commutative product of the generators of this non-commutative algebra AH bar, well then in some formal limit H bar going to 0, I recover the ordinary product of length functions. And if I take the limit of the commutator when H bar goes to 0, I'm reproducing the Poisson bracket on this space to leading order in the expansion in H bar. So these two statements are referred to as correspondence principle, here denoted CP. Well, it is known, and this I think is something going back to Kaufmann or many others, that this should be AH bar actually, I'm sorry, little typo here. It has a description in terms of generators and relations. And these relations include deformed scheme relations, so I can decompose the product of two generators of this non-commutative algebra into the generators associated to a certain product of curve, which is just defined geometrically in terms of the way they intersect by just resolving the intersection point in a suitable way, and another way of composing this. Well, okay, for reasons of time I've not drawn a picture, but that is very easy to define. And there are some more relations that describe AH bar then. So for example, there's a cubic one which looks like this, which comes from a relation in the pi1, the fundamental group of a subsurface of the surface we're dealing with. So for each subsurface embedded into the surface we're talking about, the relations of this form, and one can write them down basically explicitly for some generating set. What should be stressed perhaps is that these, I mean in general of course deformation quantization is a difficult subject. Here basically a unique answer is determined by, well, the correspondence principle plus another requirement, which is the invariance under the mapping class group. This is the natural group of symmetries that we have in the problem, which can be generated by just the so-called Dehn twists, which are described by cutting open the Riemann surface along a closed curve, twisting the boundaries by 2 pi and regluing. What this generates are the so-called Dehn twists, and whatever is generated from the Dehn twist is called the mapping class group. All right, so the next step, so this is what produces a non-commutative algebra, deforming the algebra of length functions. The next step is to talk about the representation of this algebra. And we're, unlike previous cases, of course, this is a game which was played already in the times of, well, these developments around not polynomials, Reshetikhin to AF, and so on. However, we're interested in a rather different class of representations now, which are sort of non-compact rather. Okay, so what's the point? How do we describe them? So first, let's note that it is natural to consider representations which are labeled by submanifolds of the character variety, by Lagrangian submanifolds. So such that, functions on these Lagrangian submanifolds are Poisson commuting with one another. And these are associated to maximal sets of non-intersecting closed geodesics on the curve sigma. So this is just what defines a Pan's decomposition, as has also appeared in Bertrand Inas's talk. Now, the representations that we're interested in, which are a natural class of representations, are such that the algebra is represented on now analytic functions of a certain number of variables. The number is here, it's given just by the topological data, G and N, G the genus, N the number of punctures. And it is such that these curves that define our Lagrangian submanifold or Pan's decomposition are just acting as multiplication operators with some numbers, which I can think of as being just the geodesic lengths. So in a way, really here, we're talking about, we see already, we're talking about some interesting version of quantum geometry. We're having some quantum theory where, say, geodesic length are observables, and we can talk about expectation values in certain states that these observables have. So it's a really very precise, rigorously defined quantum theory of two-dimensional geometry. The space of metrics on two-dimensional surfaces, to be precise. Well, all the other operators, which are not those in the Pan's decomposition, which have non-trivial intersection with those in the Pan's decomposition, are represented as difference operators. Let me just give you one example. So if the intersection index with one of the curves is, say, 2, one of the curves defining this Pan's decomposition, so that's this gamma S, is just 2 delta RS, so it only intersects the rth curve. Then the form will be as follows. There are some coefficients here which depend on these L's, the variables appearing here in the wave function, and the rest is this operator e to the kr is a finite difference operator which shifts one of the arguments by an imaginary finite amount. That's the type of representation that we have. And okay, it makes perfect sense. So these are unbounded operators, ultimately on some Hilbert space. Okay, so let me note here, there exist natural representations of this type, so you may ask how to precisely fix these coefficients, for example, and the claim is, but that's a non-trivial claim, which is already part of the results I'm presenting here, that there exists a natural representation denoted pi sigma, which is associated to the pairs sigma, where C is such a maximal set of non-intersecting closed curves defining a Pan's decomposition, and we need, for having really a unique specification of this representation, another piece of data, which is a triple-end graph with exactly one vertex in each pair of Pans. These representations are natural if we require that in the classical limit h bar going to 0, and then basically we have a unique answer for these coefficients here, which I was just too lazy to write, that these are determined if we require that these L and the K in the classical limit get related to the Fenchel-Nielsen coordinates, which are famous classical sets of coordinates on the Teichmüller spaces. And let me furthermore note that, say, concerning the mathematics of this representation, that, okay, we're now dealing with a representation where everybody is represented as a self-adjoint but non-bounded operator on the Hilbert space, which is L2 of R plus to the H, just the same H here as above. And it has spectrum to infinity, which is just the spectrum of values that we get when L, the geodesic length, takes real values. All right, so here's one of the first main results that was obtained after a fairly long series of works. So it is concerning the relation. So far, I was telling you, the representations are associated to Pan's decompositions. However, this would not already by itself constitute a very natural quantization of these spaces, unless ultimately the theory is independent on these extra choices of data, particularly the choice of the Pan's decomposition. It should better not be seriously dependent on the choice of the Pan's decomposition. And in order to express the invariance of the resulting theory on the choice of Pan's decomposition, we should be able to relate basically the theories associated to any given choice of Pan's decomposition by unitary transformations. In quantum mechanics, that's the way to express the equivalence between two representations of one and the same abstract algebra of observables. So, the first statement is that these representations that we've constructed are indeed all unitarily equivalent. So, if I take any pair of pan-stick compositions, well, more precisely, these slightly refined data involving the choice of the trivalent graph, then there exists a unitary operator denoted like that, such that it intertwines the respective representations. So moving pi sigma 2 of L gamma through this unitary operator makes it pi sigma 1, which is the operator, which is the representative of an abstract element of the algebra L gamma associated with pan-stick composition sigma 1. And in fact, you see what can happen is that these unitary operators exchange, for example, these operators by pure multiplication with these operators which are complicated difference operators. And so this is what this says. Okay, so this here can be difference operator if this is multiplication operator or vice versa. And so this is, of course, this is an important requirement which first of all, of course, expresses the independence ultimately of the choice of pan-stick composition, but also it gives a relation between these two pieces of data. So basically it means this guy will be essentially determined by having specified the representations. And now, well, you may ask what happens if you do round trips. If you go from one pan-stick composition sigma 1 to pan-stick composition sigma 2, then from sigma 2 to sigma 3, then there's also, of course, a unitary operator. Oh, there's another typo here. There should be sigma 1. There's also a unitary operator u sigma 3 sigma 1. And this should be almost the same. What in general quantum mechanics allows is that they're the same up to a phase. We have to allow this phase in general, but it is not really a problem. It is just a feature that quantum theory has in general, that whatever, for example, type, whatever group we have on the classical level after quantization, it may not be represented in a strict way, but just projectively. So here, this basically, we describe the symmetry transformation bringing me from one pan-stick composition to another, and it is also basically represented projectively. Now, what these transformations between pan-stick compositions generate is something which is, a mathematical object. I mean, it is just useful to formalize this passage from pan-stick composition sigma 1 to sigma 2, all of them in one go, into some gadget called modular groupoid. So it is basically the thing generated from elementary pan-stick compositions, like the one drawn here, and you just have to add, for example, a similar picture for the one puncture, the one-hole torus, and yet another generator which lives on the three-puncture or three-hole sphere, to get the generators of what is called modular groupoid. Or formally, if you want to define it, you can define it as a two-dimensional CW complex where the vertices are pan-stick composition sigma, in the sense defined before. The edges are the elementary changes of pan-stick compositions, like these ones, and then there are faces which can be described explicitly and have been described going back to the work of Murray and Seiberg and Bakalov and Kirillov and Funar and some others which I have forgotten right now. All right, so this is the algebraic structure, or the structure, the groupoid describing how to go from one pan-stick composition to another, just to have a handy language here. All right, a couple of remarks about this, what is one of the main results I want to present. So first, basically everything which appears in this theorem can be described quite explicitly. So for example, these operators can be described absolutely explicitly for the generators of the modular groupoid as integral operators with some kernels that we can write down explicitly, involving some interesting special functions like this Faddeev's non-compact quantum diagram. So some combinations thereof will represent these kernels. And furthermore, there's these data which are the projective phases, which are, well, a little innocent looking, but ultimately quite important and quite subtle. And also these data can be calculated explicitly for all the relations of the modular group coord as classified by Moore-Seiberg and then made rigorous by Bakalov, Kirillov and others. So these guys, these data are expressible in terms of a combination of the Planck's constant, this basic parameter that we've introduced in the quantization called h bar. So it is only this combination which appears, and this already suggests a relation to conformal field theory. This will be nothing but the central charge of the Liouville theory, ultimately. So this is already a very important hint, but and quite a non-trivial one if you think about it. Let me furthermore stress that what we have defined thereby is something interesting from many points of view. In particular, the notion of a modular functor was basically well, introduced to describe or introduced in a way in the two-dimensional case based on, for example, Pan's decompositions of two-dimensional surfaces. And it played some very important role in, say, Chern-Simons theory, the relation to knot theory, knot invariance, and so on, the relation between conformal field theory and Chern-Simons theory, and so on. However, there it was assumed that the spaces associated to Riemann surfaces are finite dimensional. This is part of the axiomatics if you read it in the books like Turav's book. Here what we have is an infinite dimensional analog of this, because we're talking about the Hilbert spaces that you associate to surfaces. These are here our L2 of R to the H, so it's a clearly rather infinite dimensional Hilbert space. So to rephrase what we've found in yet another useful way is we can use these operators U sigma 2 sigma 1 to define a projective local system over MGN, which is the moduli space of Riemann surfaces. Or in other words, that's what we get by dividing, by taking the quotient of the Teichmüller space by the mapping class group. Basically, the idea here is to view these guys as representing the transition functions where the patches by which we can cover the moduli space are nothing but the Pan's decomposition sigma. Well, this may be plausible because the Pan's decomposition sigma parameterized basically also boundary components in the moduli space in the Debye-Mumford compactification. And therefore, you can imagine setting up a patch around each boundary component, which is parameterized then by the sigma, and the U would describe, the operator U would describe the transition function to go from one patch to another. And so what you get in this way is just sort of trivially or tautologically a projective local system, where projective comes from the central extension that we have had, which is here. All right, so then there's a standard projective holomorphic line bundle on the moduli space of Riemann surfaces, and it is known, basically results going back to Friedan and Schenker, that if you tensor our projective local system with this projective holomorphic line bundle, then we're getting an actual holomorphic vector bundle, which is non-projective. So as opposed to a projective local system or a projective vector bundle, it can have sections if it is an honest one. So this is some object of interest, and well, basically having all this, we can define a natural Riemann-Hilbert type problem. Maybe we can ask for locally defined holomorphic, globally over MGN defined holomorphic functions which are associated to the sigmas, to the Pan's decompositions, and basically this here is the description of the passage from one Pan's decomposition to another again, in terms of an integral transformation with some kernel U sigma 1, U sigma 2, which is just a kernel representing our operators U sigma 1, sigma 2, and also multiplied here by some factor, scalar factor, which is nothing but the transition function describing the projective holomorphic line bundle EC here. So this is something which, this being non-projective, being an honest holomorphic vector bundle, though it's an infinite dimensional, it has infinite dimensional fibers, this is something which at least has a chance to have a solution, which is nothing but a section here of this holomorphic vector bundle. All right, so just very few words on what happened to prove these statements. Well, the starting point is the quantization of the Teichmüller spaces using the coordinates of Penna, Fock, Kashav, which are associated to triangulations of the surface sigma, as opposed to Pan's decomposition. So it's a rather different type of decomposition of the surface that this starts from. And so, well, these are basically, almost classical by now works of Fock, Chekhov, Fock, Kashav, and Fock and Goncharov, and then later some others. So this is our starting point. And then we're using this description, the quantized coordinates of Penna, Fock, Kashav, to construct length operators, or the quantized trace functions as functions out of these variables. So this was initiated by Chekhov and Fock, and in a certain sense completed work by myself. And then say the main part, and this is the one of the most non-trivial steps here, is to construct these operators describing the change of Pan's decompositions out of the operators that these people here have constructed, which describe the change of triangulation. And what this generates is what was then realized to be an example of quantum cluster transformations. So in a sense, one could say that here, what enters importantly is also the structure of the Teichmüller spaces as a cluster variety and its quantization. This is being used in this step in an important way. And then, another hard piece of work was to diagonalize explicitly, in fact, the maximal set of commuting length operators. And so this is what leads ultimately even to explicit formula for the kernels. For some part of the story I'm telling, it's not so crucial to have the explicit formula. However, for some other part it is, because we want to compare them to something which has a priori completely different origin. And this is what I turn to now. So now I turn to basically the B model side. All this was A model side. Now we completely switch gears and turn to the B model, that is conformal field theory. So I just want to introduce briefly or remind briefly the notion of conformal blocks. So everything basically here comes from the representation theory of some infinite dimensional Lie algebra called Virasoro algebra, which has generators Ln, integer n, and the relations written here. What we shall consider are particular representations of these algebra, representations denoted V alpha with the parameter alpha of the Virasoro algebra C. Well, it has a central extension, which I can, in irreducible representations, consider to be represented by a number, as I will do, and this number we assume to be bigger than 1 for our story. So then this representation is generated from vectors E sub alpha, which are annihilated by the positive Virasoro generators, are eigenvectors of the L0 generator with eigenvalue parametrized in a particular way. And we assume here, to introduce Q, that the central charge C is parametrized in this way. Good. Now we use these algebra in conjunction with a Riemann surface with punctures, with n punctures, a choice of local coordinates around these punctures which vanish at the puncture, and we shall associate representations V alpha R, or abbreviated VR, to each of the punctures. So the conformal blocks are linear functionals from a tensor product representations of these representations to complex numbers, satisfying the crucial defining invariance condition, which may be written like that. So they're invariant under the action of the Lie algebra of vector fields or meromorphic differential operators on the surface C, which may have poles only at the punctures. And this has a natural action on the tensor product of representations, which is defined down here, but maybe I shall not go into this in much detail. So it is basically just written out what you can really realize as the most general action that you can think of for these Lie algebra vector fields on the Riemann surface on the tensor product of representations associated to the punctures that we have on the surface. So it's these invariance conditions defining these gadgets called conformal blocks. And basically, what is well known, but we have to sort of, reiterate it here or reinterpret it a little bit, in our context is that there's a one-to-one correspondence between conformal blocks in this general setting that we're dealing with and holomorphic functions on the Teichmüller spaces. Well, first of all, let's just study an example, and just playing a little bit with these defining invariance conditions, you can show, well, the example is gen 0 for punctures, that you can express the value of the conformal block on any vector v in the fourfold tensor product, always in terms of these particular vectors. So these here are the generating vectors as introduced on the previous slide, and then we just have the action of an arbitrary number of L-1s on one of them. So this means that these numbers, which are just complex numbers, specify the conformal block uniquely, therefore. So any collection of these numbers defines a conformal block by definition. So what this means is that the space of conformal blocks is basically the dual of the space of finite Taylor series in the variable t. That's just what it is as abstractly as a vector space in this case. That is the space of conformal blocks. Now, what makes the relation between conformal blocks and holomorphic functions? We need two more ingredients. First, there is a theorem, going back, I think, to Quantization, and then in many variants proved by many others, Bayes and Teschner, and so on. It's by now, I think, textbook material, for example, in the book of Bensui and Frankel, you find a proof. It's the so-called VideoSeries uniformization theorem describing the Teichmüller space as a double quotient. We start with the algebra of, formal Laurent series in these variables tk, which are the coordinates associated to the punctures. We divide out V in, the vector fields, which are the formal, which are the, not the formal, which are the Taylor series in the variables tk, and then we divide out by the left by these mirromorphic, or, well, rather, on the surface without punctures, holomorphic vector fields on the Riemann surface. All right, so this double quotient is then known to be isomorphic, naturally isomorphic to the Teichmüller space. Furthermore, what this allows us to introduce, so this is the basis for introducing a canonical connection on the spaces of conformal blocks. So spaces of conformal blocks are the spaces of solutions to these defining invariance conditions, which were stated here. So basically, this connection can be described by saying that horizontal sections satisfy a differential equation like this, where d eta, so eta is just describing, so eta is to be identified with an element of the Teichmüller space, or a tangent vector to the modular space of Riemann surfaces, and sort of the derivative with respect to such a tangent vector, or defined by such a tangent vector, can be expressed in terms of Virasoro algebra, namely here the rho eta is defined by basically the same rule as before for any eta in this n-fold sum of Laurent series. So it is defined by exactly the same definition as was stated here. Okay, so roughly speaking, the statement is derivatives with respect to Teichmüller directions are represented in terms of Virasoro generators acting here. Furthermore, we're using here the Virasoro uniformization to basically define the map from this sum of, you can identify it with the vector fields on the unit circle to the Teichmüller space. So the connection defined in this way is known to be projectively flat, where projectiveness comes from the central extension of the Virasoro generators, which appear here in the rho eta. But the curvature, fortunately, can be trivialized at least on some open subsets of MGN. So at least in open subsets, we can hope to integrate it and to define a parallel transport in this way. Okay, so let's just sort of summarize and restate what we have reviewed here in a useful way. So first of all, Virasoro uniformization, in particular, it can be used to associate a differential operator on T of C to each eta, which is, say, in this sum of vector fields on the unit circle, which have a meromorphic continuation with a pole only at one extra point of the Riemann surface. Right? So in this invariance condition, I did not allow any extra pole except for the punctures. If I allow one extra point, well, this is a machine giving me a differential operator on the Teichmüller space, these Virasoro uniformization theorem. And secondly, let's note that the values characterizing the conformal blocks, so for example, these complex numbers defined in this way, they're now related to the values of the derivatives of what I might call the chiral partition function associated to the conformal block, which is nothing but the evaluation of the conformal block on the product of generating vectors E alpha I, like that. Why is that? Just to recall, I mean, you see here, this is the relation between, I mean, this canonical connection, I mean, the condition of horizontality defines a link between the action of Virasoro generators, and this could be, for example, the Virasoro generators which appear here in the values characterizing the conformal blocks and derivatives of the values of conformal blocks, which could be in particular, so the V, for example, could be in particular this vector E on which I evaluate to define the partition functions. So to wrap up, we observed that basically, just by definition, the conformal blocks are in one-to-one correspondence with locally defined functions on the Teichmüller space, because I can trade the derivatives of these functions for the values characterizing the conformal blocks via this machinery. And secondly, to each point y on C, I can associate the differential operator T of y on the Teichmüller space. Good. So this is abstract definition. It doesn't help very much for characterizing or computing them much more concretely than we have done so far. So there's a game to actually construct solutions to these invariance conditions, which will be very useful because it will be useful to provide a basis for this infinite dimensional space of solutions to the defining invariance conditions in a suitable sense. I should go through this very briefly. So it's a kind of Lego game which is based on the observation that we can glue Riemann surfaces by identifying angular neighborhoods of punctures. We can use this to build any Riemann surface from pairs of pens. Here's the picture, or a cartoon of how this looks like. Now, what is easy to show is that for a generic choice of this representation, the dimensions of the space of conformal blocks associated to 3 punctured squares is just 1. So there exists a unique up to normalization conformal block associated to 3 punctured square. And this means, well, and furthermore, there is a procedure then which basically lifts these gluing of Riemann surfaces to the conformal blocks. Namely, we can construct the conformal blocks on C by gluing conformal blocks on the 3 punctured square, which was basically a unique object. And this is done by summing over bases for the modules assigned to the punctures being glued. I haven't spelled out the details here for reasons of time, but that is quite canonical kind of construction. So the output will be a family of conformal blocks associated to the following data. Well, sigma is again a tensor composition as before. Then beta is, I mean, whenever we glue, we have to specify the representation that we sum over in order to perform this gluing construction. So this means that basically to each of these tubes here, which represent the gluing of 3 punctured spheres, we associate the representation. And these have labels beta. Basically, well, it's the same variables like the variables alpha that we have here to specify representations. And finally, Q here is a coordinate. So, I mean, all this depends on the complex structure on the Riemann surface we're considering. So I can parameterize this dependence by using a coordinate for a vicinity of the boundary component, which corresponds to a tensor composition sigma. So these are families of conformal blocks that have a very natural definition. Good, so here's the other main result concerning well, this side of the story, the B model. There exists I should admit, partly conjectural method. So there's one step which I do not claim to be absolutely rigorous yet. Well, I have little doubt that the result is correct, but there's some work to be done to make this really a piece of mathematics. To calculate the relations between conformal blocks from different Pan's decompositions. So the result can be written in this form. So there's a transformation between the conformal blocks associated to Pan's decomposition sigma 1 and those associated to Pan's decomposition sigma 2, where I'm integrating over all the labels of the representations associated to these tubes here, and there's a kernel W which describes this relation. Maybe let me go down here. The point is going to be that these kernels turn out to be, up to a change of variables, just the kernels of these operators U we've constructed before. And this basically is, in a nutshell, already the relation between the A model and the B model here in our story. I can phrase it in a different way by saying that the conformal blocks are nothing but sections of this holomorphic vector bundle of the modular space VGN that we have defined by the quantization of the A model in the part before. Or yet another way of saying the same thing is that the partition functions are actually solutions to the Riemann-Hilbert problem that came from the quantization of the Teichmüller spaces. All right, so this is not at all accidental. Well, here, this is a sort of summary of what we have found so far, which I shall go just briefly. So we have the conformal blocks are sections of holomorphic vector bundle VGN over the modular space of Riemann surfaces, which can be described globally in terms of their transition functions, which come from the quantization of TGN, or infinitesimally using the representation theory of the Virasoro algebra. And the horizontal sections are just these partition function of conformal blocks. Well, there's the feature, the fibers are infinite dimensional in our case. However, control is provided by Hilbert space structures that we have on the fibers. So this ultimately allows us to make here a story which is even mathematically precise. And so the perspective I want to put forward, which emerges from all that, is that in fact conformal field theory can be viewed as the harmonic analysis on the Teichmüller spaces, because it provides a decomposition of the space of functions into a certain distributional basis. And if you think a little more about it, well, just because the Teichmüller spaces are cosets of the space of diffeomorphisms of the unit circle, it is going to be related to the unknown, unexistent harmonic analysis on this infinite dimensional E group too. The partition functions play the role of the automorphic forms, because in a sense these functions, the partition function of conformal blocks, represent the basis for the functions on TGN, characterized by their asymptotic behavior near the cusp corresponding to a Pan's decomposition. I'm running out of time. What I want to explain is that this in fact can be also it's just a reformulation. We can just realize very easily that this also is just another language for describing the quantization of the Teichmüller spaces in another set of coordinates. And you can get also coordinates on the Teichmüller spaces from the metric of constant negative curvature by taking this T, which appeared in the flat connection, expanding it so the T with respect to a certain family of projective structures is defining a quadratic differential. You expand with respect to the basis of the space of quadratic differentials, and the resulting coordinate functions are canonically conjugate to the coordinate functions Q that have figured before, in the sense that the Poisson bracket, it's just the same Poisson bracket as before, is again canonical like that. So these functions, which come from the metric of constant negative curvature, are basically the second half of Dabou coordinates for the Teichmüller spaces. So then you can quantize using these coordinates, and then the T, which which classically had this expansion, of course, will turn into a differential operator, and it is easy to see this differential operator is nothing but the differential operator which appeared before. All right, so I shall conclude. Basically, in this, what you can realize is that these partition functions describe basically the kernel of the relation between wave functions in the B model and the A model respectively. So in this sense, this is the ultimately the perhaps the deepest interpretation that you can assign to the conformal blocks or their associated transition functions. They are nothing but the quantum representative of the relation between A and B model. Good, so this is well, a slide that I may not go through in full detail. I just want to point out that the conformal blocks and the associated partition functions appear in many interesting recent developments. They are known in some cases to classical special functions, hypergeometric. They are related in special cases to instanton partition functions. So this is what makes the link to the AGT story. They are related to the Yang-Yang functions in the quantum heterogeneous integral system, which in Samson Teichmüller's talk we heard about. They are related to the tau functions for isomonodromic deformations in special cases, and they are related in special cases, or probably in general, to topological string partition functions of local Calabi-Yalls. And indeed, this is some project for the future, one may suspect that in this sense the relation between A and B model actually becomes related to mirror symmetry. Well, and it is relating the subject. I mean, there are many relations of the subject to other interesting mathematical topics like harmonic analysis, non-compact quantum groups, three-dimensional hyperbolic geometry, integral models, featured moduli spaces, and the geometric Langlands correspondence. Thank you.
That's great. Thank you, Professor Teschner. The doc organizer have a present for you. Okay.
Thank you very much.
Okay, now questions, comments? Yes.
How is it in the B model? I haven't quite understood. Do you have a control of the mapping class group action, or
well,
not quite? Was it this kind
no,
of
I mean,
hesitation?
The hesitation has nothing to do with the mapping class group action. This is concerning just the technology used to calculate monodromies of conformal blocks. So this uses some operator calculus which has at a certain step basically a technical assumption that remains to be proven about basically the analytic behavior of certain vertex operators. But concerning mapping class group action in the B model, basically there's a natural way to define it, because the mapping class group is known to act by holomorphic transformations on the Teichmüller space. So basically it should just act in the natural way as deck transformations by moving the function, I mean the argument of the function to the image under mapping class group element. So,
and you cannot compare the mapping class group actions in A and B models directly if you control both.
Well, okay, so yeah, this was what I did not have the time to explain, unfortunately. So indeed, it is slightly indirect argument. The argument is, okay, there is a natural way in B model to define the mapping class group action. Now, well, I don't know if I'm allowed to go back to the slide. I think I had something there. So you see, so this is basically answering your question here. So here, this is the definition of mapping class group action. Now, we have now two mapping class group actions in A and B model respectively. If there is a relation between A and B model of this type, then of course this kernel must intertwine the respective actions. So what this means is, I mean, this is nothing but the definition of a Riemann-Hilbert type problem for this kernel, because it is a relation between what happens if I move the Q by some element of the mapping class group being related to some integral transformation on L variables. And, well, so it's a Riemann-Hilbert problem, and guess what's the solution? It's just what we've found. So, I mean, the existence of a solution to the Riemann-Hilbert problem basically is the basis for saying in this picture that there exists a relation between A and B model of this form.
Perhaps we will end this session here.